Welcome, curious minds, to a world of knowledge and discovery. Greetings, viewers. Get ready to immerse yourself in the world of Clifford analysis in this video. Clifford analysis, using Clifford algebras named after William Kingdon Clifford, is the study of Dirac operators and Dirac-type operators in analysis and geometry, together with their applications. Examples of Dirac-type operators include, but are not limited to, the Hodge operator (dd) on a Riemannian manifold, the Dirac operator in Euclidean space and its inverse on Curran and their conformal equivalents on the sphere, the Laplacian in Euclidean in space and the Atiyah and Dirac operator on a spin manifold, Rarita Schwinger Stein Weiss type operators, conformal Laplacians, spinorial Laplacians and Dirac operators on spinorial manifolds, systems of Dirac operators, the Paneitz operator, Dirac operators on hyperbolic space, the hyperbolic Laplacian and Weinstein equations. As we enter this new phase, let's uncover the impact of Euclidean space on our broader topic. In Euclidean space, the Dirac operator has the form sum ijern frac partial xj, where En is an orthonormal basis for Rn, and Rn is considered to be embedded in a complex Clifford algebra, so that this gives n where n is the Laplacian in n Euclidean space. The fundamental solution to the Euclidean Dirac operator is Rxi frac I immediate and a frax Xi, and where n is the surface area of the unit sphere CERN. Note that frac n I immediate and xi and xy, where a frac n I immediate and xi is the fundamental solution to Laplace equation for. The most basic example of a Dirac operator is the Cauchy-Riemann operator. A frac partial xi a frac partial y in the complex plane. Indeed, many basic properties of one-variable complex analysis follow through for many first-order Dirac-type operators. In Euclidean space, this includes a Cauchy theorem, a Cauchy integral formula, Morera's theorem, Taylor series, Lorentz series, and Liouville theorem. In this case, the Cauchy kernel is Gixi. The proof of the Cauchy integral formula is the same as in one complex variable and makes use of the fact that each non-zero vector x in Euclidean space has a multiplicative inverse in the Clifford algebra, namely frac saxoinma for an up to sign. This inverse is the Kelvin inverse of x. Solutions to the Euclidean Dirac equation f equals 0 are called left monogenic functions. Monogenic functions are special cases of harmonic spinors on a spin manifold. In 3 and 4 dimensions, Clifford analysis is sometimes referred to as quaternionic analysis, when the Dirac operator is sometimes referred to as the Cauchy-Riemann-Futter operator. Further, some aspects of Clifford analysis are referred to as hypercomplex analysis. Clifford analysis has a knowledge of Cauchy transforms, Bowman kernels, Schegg kernels, Plemel operators, Hardy spaces, a Kurzmann-Stein formula, and a, or Berlinghofer's, transform. These have all found applications in solving boundary value problems, including moving boundary value problems, singular integrals, and classic harmonic analysis. In particular, Clifford analysis has been used to solve, in certain Sobolev spaces, the full water wave problem IND. This method works in all dimensions greater than 2. Much of Clifford analysis works if we replace the complex Clifford algebra by a real Clifford algebra, Cl. This is not the case though when we need to deal with the interaction between the Dirac operator and the Fourier transform. Get ready for a captivating exploration as we unravel the layers of the Fourier transform and their profound significance. When we consider upper half space Rn with boundary Rn, the span of E. Under the Fourier transform, the symbol of the Dirac operator, dn sum ijern a frac partial xj, is I where in 1. In this setting, the Plemel formulas are for xy mathfren, and the symbols for these operators are up to sign a frac left frac zeta right. These are projection operators, otherwise known as mutually annihilating idempotents, on the space of Clunk-valued square integrable functions on Rn. Note that Gm sum ijern where Rj is the jth Risch potential. A frax Jackson. as the symbol of G-rin is a frac eta I zeta. It is easily determined from the Clifford multiplication that some adjourn arch. So the convolution operator G-rin is a natural generalization to Euclidean space of the Hilbert transform. Suppose U is a domain in Rin and Gex is a Planck-valued real analytic function. Then G has a Cauchy-Kovalevskaya extension to the Dirac equation on some neighborhood of U in Rin. The extension is explicitly given by some giant Teiluft x and e and n a right gexa. When this extension is applied to the variable x in e I angle xi zeta angle left if frac left up if frac I zeta a right, we get that ex is the restriction to Rin of E where E is a monogenic function in upper half space and E is a monogenic function in lower half space. There is also a Pauli-Wiener theorem in an Euclidean space arising in Clifford analysis. The time has come to unravel the secrets behind conformal structure and gain a deeper understanding. Many Dirac-type operators have a covariance under conformal change in metric. This is true for the Dirac operator in Euclidean space and the Dirac operator on the sphere under Weiss transformations. Consequently, this holds true for Dirac operators on conformally flat manifolds and conformal manifolds which are simultaneously spin manifolds. Moving on to the next segment, we have Cayley transform stereographic projection. Cayley transform stereographic projection. The Cayley transform or stereographic projection from Rin to the unit sphere CERN transforms the Euclidean Dirac operator to spherical Dirac operator ds. Explicitly, d sax left gamma n a frac n a right, wherein is the spherical Beltrami Dirac operator. Some no limits are likidlik ni ija left x I frac partial x j x ija frac partial x I right, and x in CERN. The Cayley transform over n space is y cax en x x en1 x Rin. Its inverse is x en1 en1. For a function fax defined on a domain U in an Euclidean space and a solution to the Dirac equation, then ch1 I phi is annihilated by ds on Q where Sky fraki en. Further, ds to sxs. The conformal Laplacian or Yamod operator on CERN. Explicitly, triangle S equal triangle Albfrac 1 Fornen, where LB is the Laplace-Beltrami operator on CERN. The operator S is, via the Cayley transform, conformally equivalent to the Euclidean Laplacian. Also, d sx is the Paneitz operator. SS2. On the n-sphere, via the Cayley transform this operator is conformally equivalent to the bi-Laplacian. These are all examples of operators of Dirac type. As we enter this new chapter, let's navigate the complexities of Weiss transform and unravel its multifaceted nature. A Weiss transform over an Euclidean space can be expressed as a fracaxobxtwera b, c and d till n and satisfy certain constraints. The associated matrix is called an orthosvolon matrix. If I max fracaxobxt and phi equals 0, then Xfmax is a solution to the Dirac equation where Gmax frac y tilde x Dirac Stern and is a basic antiautomorphism acting on the Clifford algebra. The operators Dirac or Nurk when k is even exhibit similar covariances under Weiss transform including the Cayley transform. When axob and x are non-zero they are both members of the Clifford group. As a frac x frac x bxd, then we have a choice in sign in defining x. This means that for a conformally flat manifold M we need a spin structure on M in order to define a spinor bundle on whose sections we can allow a Dirac operator to act. Explicit simple examples include the n-cylinder, the Hopf manifold attained from n Euclidean space minus the origin, and generalizations of k-handle toruses obtained from upper half space by factoring it out by actions of generalized modular groups acting on upper half space totally discontinuously. A Dirac operator can be introduced in these contexts. These Dirac operators are special examples of assessing the Dirac operators. Moving forward, we'll be taking a closer look at a Schwinger Dirac operator. Given a spin manifold M with a spinor bundle south and a smooth section X in south n, in terms of a local orthonormal basis X, in X of the tangent bundle of M, the Schwinger Dirac operator acting on S is defined to be at saxa sum ijern ija tilde gamma e ijoxasexa, where is the spin connection, the lifting to south of the Levi-Civita connection on M. When M is an Euclidean space, we return to the Euclidean Dirac operator. From an Schwinger Dirac operator D we have the Lichnerovich formula. De gamma gamma for tau is the scalar curvature on the manifold, and is the adjoint of. The operator D is known as the spinorial Laplacian. If M is compact and somewhere, then there are no non-trivial harmonic spinors on the manifold. This is Lichnerovich theorem. It is readily seen that Lichnerovich theorem is a generalization of Liouville's theorem from one variable complex analysis. This allows us to note that over the space of smooth spinor sections the operator D is invertible such a manifold. In the cases where the Schwinger Dirac operator is invertible on the space of smooth spinor sections with compact support, one may introduce Cax yd1y xym, where y is the Dirac delta function evaluated at y. This gives rise to Cauchy kernel, which is the fundamental solution to this Dirac operator. From this one may obtain a Cauchy integral formula for harmonic spinors. With this kernel, much of what is described in the first section of this entry carries through for invertible Schwinger Dirac operators. Using Stokes' theorem, or otherwise, one can further determine that under a conformal change of metric the Dirac operators associated to each metric are proportional to each other, and consequently so are their inverses, if they exist. All of this provides potential links to Schwinger index theory and other aspects of geometric analysis involving Dirac-type operators. Let's now turn our attention to hyperbolic Dirac-type operators and uncover the fascinating insights it brings to the table. In Clifford analysis, one also considers differential operators on upper half space, the disk, or hyperbola with respect to the hyperbolic, or Poincare metric. For upper half space, one splits the Clifford algebra Cl into Cl plus Cl n. So for a in Cl n, one may express a as b plus n with a b in Cl. One then has projection operators p and q defined as follows: p equal b and k equal c. The Hodge operator acting on a function f with respect to the hyperbolic metric in upper half space is now defined to be frac and f. In this case, Murph triangle and perfracnax and a frac partial x and left triangle and a perfracnax and a frac partial x and fracnax and a right n. The operator triangle and if fracnax and a frac partial x n is the Laplacian with respect to the Poincare metric, while the other operator is an example of a Weinstein operator. The hyperbolic Laplacian is invariant under actions of the conformal group, while the hyperbolic Dirac operator is covariant under such actions. Our focus now turns to Rarita Schwinger Stein Weiss operators, an important aspect of our discussion. Rarita Schwinger operators, also known as Stein Weiss operators, arise in representation theory for the spin and pin groups. The operator Rk is a conformally covariant first-order differential operator. Here k equals 0, 1, 2. When k equals 0, the Rarita Schwinger operator is just the Dirac operator. In representation theory for the orthogonal group, on it is common to consider functions taking values in spaces of homogeneous harmonic polynomials. When one refines this representation theory to the double covering pin of on, one replaces spaces of homogeneous harmonic polynomials by spaces of k-homogeneous polynomial solutions to the Dirac equation, otherwise known as k-monogenic polynomials. One considers a function fax, u where x in u, a domain in Rn, and u varies over Rn. Further fax, u is a k-monogenic polynomial in u. Now apply the Dirac operator dx in x to fax, u. Now as the Clifford algebra is not commutative dx u, then this function is no longer k-monogenic but is a homogeneous harmonic polynomial in u. Now for each harmonic polynomial hk homogeneous of degree k there is an Ullmann-Fischer decomposition. H cox P cox Kx, where Pk and Pk are respectively K and monogenic polynomials. Let P be the projection of Hk to Pk, then the Rarita Schwinger operator is defined to be Pdk, and it is denoted by Rk. Using Euler's lemma, one may determine that the Pk K1. So, Rk left I fracant Od right X. As we venture forward, let's take a closer look at conferences and journals and its impact on our understanding. There is a vibrant and interdisciplinary community around Clifford and geometric algebras with a wide range of applications. The main conferences in this subject include the International Conference on Clifford Algebras and their applications in mathematical physics (ICCA) and applications of geometric algebra in computer science and engineering (GACSE) series. A main publication outlet is the Schwinger journal Advances in Applied Clifford Algebras. Remember to follow me on social media for behind-the-scenes content and updates.